Hello, I'm Alastair Hales, a researcher in the Electrochemical Science and Engineering Group at Imperial College London. I'm a member of the team working on TOPBAT, our Faraday-funded industry sprint project. I'll begin today discussing the background to the project before moving on to our methods and expectations. Objectively, we are investigating how to design pouch cells for better thermal management, and we are integrating our battery models with our work on the cell cooling coefficient. We believe a lack of communication between the tiers of the battery industry has created a suboptimal system. This assumed battery pack designers select cells based on the performance metrics available to them. Because there is no metric to define the thermal management capability, pack designers often revert to choosing cells with the best energy density, and this drives competition for cell manufacturers to maximize energy density at the expense of thermal performance. In the end, over-engineered thermal management systems are required to combat this problem. At cell level, energy density may be optimized, but at pack level, it certainly is not. The cell cooling coefficient is a standard to define a cell's capability to be thermally managed. It defines the thermal gradient that will build up across a lithium-ion cell as a result of a certain rate of heat removal. A pouch cell would have a CCC value for surface cooling and another for tab cooling. The CCC can be used as a metric to highlight the suboptimal system that we have presented and as a design tool to overcome the problem. We will demonstrate this as part of the project. We're looking to increase the cell cooling coefficient for our test cell and understand how this impacts the performance of the cell in operation. The problem with surface cooling, currently the dominant thermal management method used in industry, is the layer-to-layer temperature gradients that build up. They cause uneven loading in the cell through a driving cycle, reducing accessible capacity and fast charge capability. Over time, this increases the rate at which the cell degrades. These problems can be solved with tab cooling, simply by changing the direction of thermal gradients in the cell. Unfortunately, tab cooling is not usually viable in cells as they are designed today. Tabs are less than 0.5 millimeters in thickness and often located right next to one another. Required rates of heat rejection cannot be achieved in operation. Prior studies have shown that thick tabs are the key to unlocking the thermal bottleneck that currently exists in pouch cells. Dr. Yan Zhao, currently an entrepreneurial fellow with the FI, highlighted this in his PhD, and we've just had a paper accepted by eTransportation that draws similar conclusions. The 20 amp hour pouch cells manufactured for this project by Power have tabs located at opposing ends. We have cell models available, one with 0.2 millimeter thick tabs and another with 0.5 millimeter tabs. We'll be parameterizing and validating our ECN model for these cells, and we will use this model as a design tool, varying tab thickness to examine the effect on the cell cooling coefficient. We are looking to discover a cell design fit for operation with a tab-cooled thermal management system. We do not think our 0.5 millimeter tabs will be sufficient for tab cooling. Although our thermal models predict a substantial rise in the cell cooling coefficient, our initial cycling data suggests significant thermal bottlenecks still exist. The reason for not going thicker during this project is simply one of achievability. Given the short time frame for this project, it is essential that we have operational cells to demonstrate the functionality of our model design methods. Extrapolation of the tab thickness in the model will be possible by the end of the project, so we'll be able to define the required thickness for tab cooling in the future with these cells. By the end of the project, we hope to make hypotheses on thickness required for the power cell. We will provide this as a model result with a threshold CCC value above which we believe tab cooling becomes a viable thermal management method. These tabs may have a thickness in excess of 1.5 millimeters, and therefore we are also conducting a study on how to weld the tabs and how to manufacture a pouch seal that meets industry standards. We will use our modeling methods to evaluate the impact of further geometric change on a cell's thermal performance. How else are we able to improve thermal management and further increase energy density, power density, and cell lifetime? Finally, we will look towards the next steps of impact. In what application is tab cooling most advantageous? We will be looking at the economic benefits, the safety, and the real-world operating temperatures of various applications as a way to begin to answer this question. Thank you very much for taking your time to listen today. I look forward to answering any questions.